Hey, in the third part of this introduction, I would like to talk about layering in the context of networks. So, networks are complex uh, structures, right? There are lots of different components to them. The hosts, routers, different links that connect different routers or packet switches. We have the applications that use the services provided, the protocols they implement at different levels, and so on. So the question is, how should this be organized? How should we model it? How should we reason about it? How do we manage this complexity? Key approach is to use layering. Okay. So layering here means to subdivide the required functionality of the system into different layers that interact with each other through a well-defined way. Okay. We identify the different pieces of that complex system, we assign a responsibility to each part, and we define how they interact with each other. Um, the different uh, like groups that perform a similar task are placed together at a layer, and we refer to them in the reference model I'll be talking about in the next slide. This provides modularization, but it is different from just having simple modules like you may have in a complex software system, because each of these modules also also forms a layer which has a principled way of interacting with other modules. So this is not arbitrary. Layering allows each part of the system to have a well-defined responsibility, and very often that's good because it leads to modularization and encapsulation. In some cases, though, it involves trade-offs, a compromise. Perhaps the system could be implemented differently if strict layering were not followed. Okay, so sometimes layering is considered harmful. Layering is not something that is restricted to networking, right? So we also know layers, for example, at the software stack. An example is between the user applications and the operating system kernel, right? That is an example of using layering that interact with each other at the system called boundary, like we talked about in previous lectures. So let's talk about the so-called reference model, and it shows the major layers and what each layer means and what it does. So at the top, we have the so-called application layer. Okay, so the application layer is also referred to as layer 5, or also called layer 7. We'll see in a second why that is. Um, then the transport layer, layer 4, layer 3, layer 2, or layer 1. Actually, most of the time the application will be layer 7. So the application layer is this layer where network applications are implemented, right? The things that users care about. Web pages, for example, the HTTP protocol, SMTP protocol to send email, IMAP protocol to access email, so additionally a protocol to do that. So they provide the actual applications that users care about. At the transport layer, we have protocols that implement the data transfer between different processes. There are two widely used protocols that fall into this layer, TCP and UDP. TCP provides reliable, in-order data transmission, and UDP provides unreliable, datagram-based data transfer between different processes. Those are the most widely used transport layer protocols in the internet today. So then layer 3 is the network layer. And the task of the network layer is to make sure that datagrams are sent from the source to destination, make it there, right? The most widely used protocol, in fact, the only widely used protocol here is IP, the Internet Protocol. But that the network layer is also where routing takes place. That is the management of making sure that everyone knows which path a packet has to take through the network to reach its destination. Then under the layer 2 is the so-called link layer that governs the data transfer between neighboring elements in the network. So the protocol that makes sure that data can be sent from one hub to the next one. Examples include Ethernet, the Wi-Fi wireless protocols, other protocols such as PPP, which is point-to-point protocol. And then the lowest layer is the so-called physical layer, and those are the electronic specifications um, that make it so that the data can be exchanged across one link across a specific medium, right? Such as optical cable and so on. Why did I stumble here a little bit about whether the application layer is layer 5 or layer 7? Um, this comes from an historical effort called the OSI ISO reference model. It's by a group of people called the Open System Interconnect Initiative under the auspices of the ISO. In fact, there was an attempt, and it was in the late 1980s, 1990s, where people wanted to design a networking stack for all users, right? And so there they created a reference model that defined a number of layers and then started to define protocols at each layer. And this is where the physical layer became layer 1, link 2, network 3, transport 4. But then they envisioned there be two other layers, layer 5 and 6, to deal with things such as how to present data that is being exchanged between applications, or also to do session management. So those layers actually did not find um, implementations that uh, were grown organically. So typically application developers would fold these services into their application layer, and the OSI ISO protocols never took off. So this is why these two layers essentially sort of disappeared, and application then became the fifth layer, layer 5. But traditionally, the application layer is layer 7. So if you hear layer 7, that means the application level. This effort, by the way, by the ISO, OSI ISO, never really took off. For a number of reasons related to political reasons, financial influence, and essentially people trying to define protocols for which there were no implementations yet and that hadn't actually proven themselves. This is very much different from the more organic process that I talked about, the way the internet grew by allowing everyone to put out RFCs and making proposals as to how things should be done. Nevertheless, the numbering of these layers has survived. I'd like to talk about the relationship between layers, services, and protocols. So we say that a layer provides a service to an upper layer. In order to provide this service, it engages in a protocol with its peer entity at the same layer and uses the services provided by the layer underneath it. Here I'm putting this illustration is from a book by Tannenbaum that I added to this slide set to show this relationship. So in a system that uses strict layering, the, the two entities at layer K can communicate with each other and implement the protocol at this layer only through layer K minus 1. So if data needs to be exchanged, it is passed from layer K to layer K minus 1, and then maybe to a lower layer, and at some point it goes across the wire, and then it goes back up this layer here. But layer K does not directly interact with layer K minus 2, kind of K minus 3, and so on. And layering also means that the service that this layer provides, layer K plus 1, is the service that layer K plus 1 uses to implement the service that it provides to higher layers. Okay. So this is the relationship between the service provided by a layer, the layer itself, and the protocol that is the exchange of messages between entities at this layer. When layering is implemented, then the messages that are exchanged at one layer are encapsulated as they're being passed to lower layers. It's very important to understand. And the Kuros and Rossi have created a nice animation that I would like to walk you through to explain this encapsulation process. So here we're using the simplified TCP/IP reference model with application transport and so on layer. Suppose we have an application at the source that wants to send a message to an application at the destination host. This message might be something like get get me a web page, right? Would retrieve a web page as an example. So in this case, the source would pass this message to the lower layer, say the transport layer in this case. And the transport layer now would be responsible for sending this message to its peer on the other side. And along the way, performing the transport layer services, for example, making sure that the data transfer is reliable, making sure that there is a retransmission if this particular message is lost. To do this, the transport layer has to prepend a header with additional information that is relevant needed by the transport layer. So this header is prepended, and the resulting packet now has a different name. It's no longer called a message, it's called a segment. So the generic term packet here is replaced with more specific terms at each layer. And at the transport layer, we typically talk about segments, particularly in TCP. So we now have a segment with a header, transport header. That header may have information such as which application it's for, that this message should be sent to. That was information that the application gave to the transport layer when it asked to send this message. Now the application does not need to explain to the transport layer what's in that message. The message itself is opaque to the transport layer. It just treats it as a number of bytes, which is why it is prepending its own information at the beginning. Then the segment is passed to the network layer. Okay. So the network layer now receives it, and it's also given information where the data should be sent, an IP address, for example. So it will prepend a header with network information, and then we say the thing is called a datagram. The network layer then will pass this information to the link layer. The link layer does the same thing. It will prepend some information, and this is then called a frame. And so link layer might have identified that this particular datagram needs to be sent out a certain link to a certain destination. So now watch what happens next. The link layer will pass it to the physical layer. In this case, the packet actually made its way through part of the network already to the next network element. This is the role of a so-called switch. So switch are network elements that do not perform processing at the network layer. So in this case, if let's say the link address says that it needs to be sent to this particular router, these networks will do this automatically without performing any layer 3 processing. Switches is what is used to connect, for example, different parts of an Ethernet together. In fact, you can buy them at the Best Buy, and you can wire them together in an arbitrary topology, and frames will be transmitted. So these switches use a protocol among each other to learn about where to send things, but none of this involves layer 3. Now the switches themselves, though, they will look at the information at the link layer, right? But this process is typically done in hardware, and then the corresponding forwarding as well. It's called a switch. Or specifically a switch, when people say switches, this is what they imply, something that does an automatic forwarding without requiring layer 3 activity, as opposed to a router where processing at layer 3 takes place. So this router here now has received this particular frame on its, let's say, Ethernet interface, and it passes this up to the network layer. So to do that, it will strip the link header from it, passes it up, and so now the network layer will look at the network header, which contains the information about where to send this particular datagram. And let's say the network layer may decide it needs to be sent out to this link. And to do so, it will send it to the link layer that goes with this link, which will prepend another link header and then send it to the destination. So the destination receives the link header, and it will then examine it. Okay, so first it will receive the link and pass it to the network layer. The network layer here in this case would look at the destination address, would say, well, where does this packet go? In this case, it would realize, oh, that's a packet for me, so it will not send it on, but rather it will pass it on to the transport layer after stripping that network header that is now no longer needed. The transport layer, in turn, will look at what it receives, and it identify the header that was placed here by its peer at the source. And this header will have the information about which application this message is for. In TCP, we're using something called a port number, which you will be using when you're doing this, when you're implementing your network applications. So it decides that this needs to be sent to this application. It will strip the header and send the original message to the application. So this type of encapsulation makes it so that the actual message that is sent by one layer to the layer below it is opaque data, and each layer prepends information that it needs to perform its function to the um, to the packet, right? And the packet is then known by different terms: message, segment, datagram, frame, um, in this order. So this was how encapsulation works. Um, Let me mention one other thing that you may encounter. This is so-called hourglass view. So even though layering means that I could use different protocols at each layer as long as I provide the same service, right? The type of protocol that is being used as at one layer is independent of the service that this layer provides. So even though theoretically it's possible to have different protocols at each layer, in practice, it turned out that some layers have lots of protocols and some layers only have a few. In fact, the network layer, there's one dominant protocol today, that's IP, though it comes in two variants, IP version 4 and IP version 6 that we'll talk about. The transport layer, we have two dominant protocols, UDP and TCP. They're not the only ones, but they're dominant. But we have lots and lots of variety at the application layer and at the host to network layer. But all of these typically go through the same use the same network protocol, the IP protocol. And in part, that's because, of course, the IP protocol is the one that is used by the capital I internet that we are all connecting to. Last slide. So I so far talked about layering in terms of the model, right? How do we achieve encapsulation? How do we separate the protocol that's used at one layer from the services that it provides? How does one layer treat the data it receives from another layer in an opaque fashion? But how is this actually implemented in a concrete system typically? Well, there the parts of the implementation involve um, user applications, user processes like the one you will be implementing, are typically ones that implement the application level protocols. But the transport and network implementation is typically inside the kernel. Not always, but typically the case. So there has to be a way for user application to access this networking implementation. And this is through something called sockets. So sockets provide the interface that user applications can use to access network services. And so to initiate this, to send data, for example, a user application would perform a system call, enter the kernel, and then the data here would be passed through different layers in the kernel that each may be prepending headers, given from the TCP layer to the IP layer, and from there to some specific network device that is then used to send out the information. And the opposite path, the transfer needs to take place as well, but there's a little bit more subtle because the question is in what context the necessary processing should be performed. Typically, what happens is if data arrives on a network device, an interrupt will be triggered. The kernel will run this interrupt, and it will, let's say, just receive this packet, maybe save it somewhere or acknowledge it from the network device. But then additional protocol processing may have to take place. For example, TCP demands that for certain packets, a response is being sent to acknowledge that the package was received. This processing would also take place at the kernel level, but it's typically not done immediately, but it is delayed in something called a software interrupt. Now, eventually, when a packet is received, the application will need to be notified. So, for example, the application may have already called read or receive to trying to receive this packet, and it may be in a blocked state. So in this case, it is the responsibility of the networking implementation to unblock this application so it can wake up and then receive this packet and send it to the user level so that the user application can then take care of processing this packet. So we see that this that the implementation of these networking protocols, this networking stack, also involves an interaction across different layers in our typical software stack, and in particular involves the user kernel level system call boundary that we devote most of our attention to in this systems class.